So next we'll go into chapter 12, sections 1 to 2, using chi-square for goodness of fit, and then we'll do in 12.2, it's chi-square for goodness of, or for independence. It sounds really complicated, but when you use StatCrunch, it's not really that bad at all because it does all the work for you. Okay, so let's look. So the goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. So we're given a frequency distribution, and the question is it the same as another specific distribution? Is it a good fit to use that distribution? That's why it's called goodness of fit. And we're going to use a new distribution called the chi-square distribution, which we'll talk about when we get there. So that's why it's called goodness of fit. Does it fit the model? So here's a simple example. According to the manufacturer of M&Ms, 13% of a plain bag should be brown, 14% yellow, 13% red, 24% blue, 20% orange, and 16% green. A student randomly selected a bag and counted the number of each color and obtained the results on the table. So wrote down how many brown, yellow, red, blue, orange, and green. So we want to test whether these plain M&Ms actually follow the distribution stated by the manufacturer at the alpha equals 0.05 level of significance. So does it follow that 13%, 14%, 13%, et cetera model? That's what goodness of fit means. Does it follow some other model? Another example. An obstetrician wants to know whether the proportion of children born on each day of the week is the same. So she randomly selects 500 birth records and obtains the data that's in the table. Is there a reason to believe that the day on which a child is born doesn't occur with equal frequency at the alpha equals 0.01 level of significance? So we're going to compare this to a model where the numbers are the same instead of being different. And then if the model is that they're the same, and this is, see how different this is from that. So a little bit about the chi-square distribution. And I mean a little bit. It's not much you need to understand about it. So that letter chi is another Greek letter. And so this is called chi-square, and it rhymes with sky square to help people read it from a book. And it represents the values of the chi-square distribution. It's used to determine whether there's a statistically significant difference between the expected frequencies and the observed frequencies in one or more categories of a contingency table. So are things as expected or not? So in the next section, we're going to use it to determine if two variables in a contingency table are independent. But right now, we're going to be looking at, are two different models the same? It's not symmetric, obviously. Its shape depends on sample sizes. That's what the colors are about. You're going to see, and if you go look in the book, or if you hit help me solve this, you're going to get this formula. It's observed minus expected squared over expected. It's horrible calculations. Luckily, StatCrunch does it all for us, so it's very simple. But when we're talking about observed, it's what really happened, what does the data say, versus what's expected by the model. So our hypothesis test with chi-square is our null hypothesis saying the two proportions or the two frequencies are the same, that everything's the same, and H1, the alternative, is that they're different. So if I went back to the examples, this model with the M&Ms, the null hypothesis says that these frequencies are the same as the M&M frequencies, the percents they gave us. Oops, sorry. And the alternative would be no, they don't match up. They're not the same. They're significantly different. We don't know how they're different, just that they're significantly different. And then for the obstetrician model, the model she suggests is that there's the same number of births every day of the week. The Null hypothesis says, yes, there are the same number of births every day of the week. And the alternative is no, there aren't. There is a significant difference between that model and what happened in our data. So going back to the M&Ms model, according to the manufacturer of M&Ms, we had 13% brown, 14% yellow, 13% red, 24% blue, 20% orange, and 16% green. In this example, what we're comparing is a frequency of each color to a percent of each color. When you use the formula, as you'll see if you want to look in the book, they have to change all those percents to frequencies. So they convert it by taking a percent of the total to get frequencies. But StatCrunch does it all for us because we love StatCrunch. So here's how we do it in StatCrunch. We have to enter the data into a table in StatCrunch. There's too much to just fill in during the calculation. So you need an observed column and you need an expected column. The observed means from the data. What did the data tell you? So this is the data column, and they call that the observed. And the expected is from the model. So our observed numbers were from the table on the other page, and the expected were from the percents on the other page. I put the colors in to make sure I was putting them in the right row, but you don't have to put a color column, but I decided to do that. Okay? So you need a column with observed and a column with expected, and they line up, the browns together, the blues together, etc. Your next step is to go into StatCrunch and do stat goodness of fit chi-square test. Okay? You choose your observed, and that's why I call the column observed, because it's easy to find it. And you choose your expected. And you ask on the bottom to display the expected right here. Okay. So our output with this chi-square test is it tells you your n's, that's your sample size. It tells you the chi-squared test statistic. So this is the test statistic. It's not a z-stat or a p-stat now, or a z-stat or a t-stat. It's now a chi-square. So a chi-square stat. And then we get a p-value. So our p-value is high, 0.24, which is more than alpha equals 0.05. So we cannot reject the null. So we don't have sufficient evidence to say there's a difference between the model from the company and the actual number of M&Ms we got. Okay, so the only thing this can tell us is if there is a difference, but we don't have enough evidence to see a difference. Now notice this column that says expected. This is the calculated for you. The percent turned into frequencies. So the total number of these is 400. And we were given percents for our expected, and that's what I put in the expected column. They turned those percents into frequencies by taking the percent, multiplying it by 400, which is our sample size, and popping out our expected. So in some of the homework, they ask you to do the expected because they want you to calculate it, but you don't need to calculate it because StatCrunch does it for you. So if the percents lined up from the M&M company, we would have expected 52, I think that was brown, and we got 57. Not too far apart. And 56 of the next color, but we got 64. We expected 52, but we got 54, etc. So these aren't different enough to say that this is a really different bag.